Hello, and welcome to my demonstration of a PID controller with a self-balancing robot. The following is a block diagram showing the combination of a 3-axis accelerometer and 3-axis gyroscope, which are on the MPU 6050, and the microcontroller Arduino Uno, as well as the L298 dual H-bridge. The MPU 6050 outputs an I2C signal at a frequency of 400 kilohertz, which tells the microcontroller yaw, pitch, and roll, as well as the angle that it's at, which is important to give feedback whether or not the robot is balancing. The microcontroller then interprets that data and sends it to the dual H bridge in order to pivot the motors forwards or backwards. This is a circuit diagram, which is equivalent to the one that I'm using. I found this online, and it had some 18650 lithium-ion batteries, similar to the original YouTube video, but I chose to replace this with AA batteries because it was more easy to access. The AA batteries give me a voltage of about 6 volts, and the 18650s have a nominal voltage of 3.7. So the 18650s have a little bit higher voltage than I used, but overall I found that that wasn't a problem, and this circuit design works. First, what I did for this project is look at some references that were online, and I came across this video about a self-balancing robot. And I realized that a lot of the components that were here were readily available at FAU. And so this would be a project that would be something that I could replicate in the time scale of our class with minor modifications. And the code is in Arduino IDE, and it uses the proportional integral derivative controller just like we do in our class. And so the next thing that I did was find a body like this on this website called Thingiverse that would be compatible with components. Like we have these motors, and we also have the motor controller, and we have an Arduino. And so I found this, and then I 3D printed it. I went online and I got all of the required libraries for this project, which are the proportional integral derivative controller, the MPU 6050, the accelerometer and gyroscope, the L298 motor controller, and the I2C library. And I downloaded those um, to my Arduino IDE. This code right here is actually showing what the accelerometer prints out by itself. But this is the self-balancing robot code, which uses the libraries that I just mentioned. So this code um, initializes I2C and sets a minimum speed for the motors. Um, and then it has a yaw, pitch, roll data type, which sets the original set point and uses a PID controller in order to make the robot adjust itself to this original set point. So down here, you'll see that we actually take that input data, that input value, and then we take the yaw pitch roll and we multiply it by 180 over pi, and then we add 180 to that. So this is basically converting radians to degrees and then adding 180 degrees. So what this means is that 180 degrees is level with the surface. It's like parallel with the surface, the way that I set up the accelerometer. And so I actually ended up going with a set point that was slightly less than 180, 177, because my robot has a bias. So it wants to lean forward, but this set point actually helps it lean back, which can help it gain stability. And these are the KP, KD, and KI values, which I used in order to make the robot balance the way it does. In addition to this, there's motor speed factors that you can adjust. And so you can specifically slow down or speed up the motors with this scaler. And then this is what the rest of the code looks like. If you're interested. This is one of the best videos that I have of the robot balancing, and my friend Aaron's there kind of perturbing it a little bit. And so this is the best way that the robot works. It wants to fall forward on its own, but it balances.